And today's section is going to be about solving right triangles. So that's where you're given a couple of the measurements of the angles, a couple of the side lengths, and you have to solve the rest of the triangle. And now that we've learned about sine, cosine, and tangent, and we've learned about the Pythagorean theorem and these different properties about side length, we're able to do that. But just as a quick reminder, I want to first go back and see which of these acute angles have a cosine equal to 0.5. Just as a quick little, refresh of what we've been doing because we haven't done some math in pretty much a week. So if we have this right triangle here, we're going to call this guy A, B, and C. And our right angle is already, you can see that it's going to be at angle C. And we're given some side lengths here. So our hypotenuse has a length of 2, our short side has a length of 1, and our longer side has a length of root 3. And now remember, we're looking to see what the cosine is here. So remember that the cosine, if we go and look at cosine, cosine is adjacent over hypotenuse. So we have two acute angles that we can look from here. We have this acute angle right here, angle A. We also have this acute angle here, angle B. So why don't we just start with the cosine of A. So the cosine of A is going to be the leg that is adjacent to angle A, as well as the hypotenuse. And so the leg that is adjacent is going to be this one that's touching right there, or this square root of 3. And then we're going to divide that by the hypotenuse, or the square root, or sorry, just a whole 2. And if you were to divide that out on the calculator, you'd approximately get 0.8660. Likewise, we can do the same thing and try to find what the cosine of B is. So the cosine of B is going to be the adjacent over the hypotenuse. And if we look at angle B here, the leg that is adjacent is going to be this leg that is equal to 1. Once again, our hypotenuse is going to be equal to 2, and 1 divided by 2 does indeed equal 0.5. So in this specific right triangle, the cosine of B is equal to our 0.5 that we were looking for. And so that was just a quick little reminder of how cosine works. Sine works very similarly. Tangent works very similarly. Remember, you can always remember sine, cosine, and tangent by using SOHCAHTOA. And the S stands for sine. Here, let me grab a highlighter here. The S here stands for sine, the C stands for cosine, and the T stands for tangent. The O stands for opposite, so those both have opposite. The A stands for adjacent, and then the H stands for hypotenuse. So that's what SOHCAHTOA means. But moving on, we're going to go ahead and we need one more little piece of information before we can start looking at solving right triangles completely. Because sometimes you're given what a sine ratio is equal to. You can find that out by looking at these side lengths here, but you don't know what the angle is equal to. So wouldn't it be nice if we were given some side lengths and able to find what the angle is equal to? So if we have this right triangle here, ABC, and we're going to say that angle C is our right angle, and we're going to let A, specifically angle A, be an acute angle. All right, we're going to define some things that are going to be able to help us find some angle measurements. So first is going to be the inverse of tangent, or the inverse tangent. And so the inverse tangent is if the tangent of angle A, so this angle A right here, if the tangent of A is equal to x, then the inverse tangent, which is written as tangent with a -1 exponent of x, is equal to A. And by A, I mean the measurement of angle A. So it's just flip-flopping this x and this A and adding the -1 there. And so in this specific example, if we highlight our sides here, if we look at angle A, remember tangent is TOA, so it's opposite over adjacent. So the tangent inverse of the opposite over adjacent, so the opposite would be BC, over the adjacent AC, is going to be equal to the measure of angle A. And it might be nice if I added some color to this for you guys, so why don't I do that real quick. We'll make BC red, we will make AC green, and then we'll make AB blue. So I will go ahead and rewrite that just a second for you. BC over AC, BC is going to become red, and AC is going to become green. Likewise, we can have what is called an inverse sine. So it's going to be the same exact thing, except instead of working with a tangent ratio, we're going to be working with a sine
Charging
ratio.
battery.
Oops, sorry, I forgot to unplug my headset. So if the sine of A is equal to y, right? A cannot be equal to x anymore because we use that for tangent. So the sine of A is going to be equal to y. Then the inverse sine, written as sine with a -1 exponent of y, is going to be equal to the measure of angle A. And now remember, sine is equal to opposite over the hypotenuse. So our opposite leg of angle A is going to be BC. And we're going to divide that by our hypotenuse, AB. And we're going to get that the sine, inverse sine, sorry, I forgot to put the -1 there. The inverse sine of BC over AB is going to be equal to the measure of angle A. And then finally, we can have our inverse cosine. Which is going to be just like sine, just like tangent, except now we're using a cosine. So if the cosine of A is equal to Z, then the inverse cosine, written as cosine with a -1, of Z is equal to the measure of angle A. And so the cosine inverse, and remember now, cosine's adjacent over hypotenuse, so our adjacent is going to be that green leg, AC, divided by our hypotenuse, which is going to be that blue leg, AB. And if we divide those two, plug it into an inverse cosine on a calculator, you will get that that is equal to the measurement of angle A. All right, so now we're going to do a quick example. I want to show you on a calculator real quick where you can find inverse sine, inverse tangent, inverse cosine. Every calculator is different, so just be wary of that. We're going to approximate the measure of these angles using a calculator. So if I'm giving you that the tangent of an angle A is equal to 0.75, we want to find what this A is equal to, what that angle measurement is, right? Because you plug an angle into a tangent. And so now all we need to do is take the inverse tangent of our answer, so tangent -1 of our answer 0.75, and that will give you the measurement of angle A. And so if we go to a calculator here, I'm going to just use the Desmos calculator. Oh, where's that? There it is. So the Desmos calculator, I love it. And inverse tangent on the Desmos calculator, you could either type it in manually, or you can go over to functions right here, go tangent inverse, back to your main, type 0.75, clothing parenthesis, and our answer is going to show up here on this right side. It's going to be 36.869. You know, it goes on forever. So the inverse tangent of 0.75 is going to approximately equal 36.9 degrees. And now we can go through and do this for some other measurements. I don't want to go ahead and slow things down today. So the sine of B, let's say the sine of B is equal to 0.87. On a calculator, we would type in the inverse sine, so with the -1 is equal to 0.87 is approximately equal to, if you type that in on a calculator, you should get 60.5 degrees. And then finally, the cosine of C is going to be equal to 0.15. If you type in cosine inverse of 0.15 into a calculator, you'll approximately get 81.4 degrees. And real quick, I'm going to go back to our calculator here. And I want to highlight right here above the number pad. You see this degree? I can click it. It goes over to rad. So we have deg or rad. Make sure your calculator says deg, degrees. Right? If you switch over to radians, you're using different angle measurements. And if we retype this in, you can see the answer changing. Right? You don't want an angle measurement of 0.640. You want an angle measurement of 36 degrees. So that is the difference there between degrees and radians. Very important. Make sure you have your calculator set to degrees. All right, so now we're going to build up to what we've been doing this for. This is to solve a right triangle. All right, to solve a right triangle, means to find all unknown side lengths and measurements. All right, you can solve a right triangle if you know the following. If you are given only 2 side lengths, you can solve a right triangle. So you can find all 3 angles from that and the missing side. Or if you're given 1 side length and 1 acute angle, you can solve the right triangle. Make sure you're doing your acute angle. If it's just the right angle, you can't solve it. All right, all the triangles that I give you for practice, they'll all be solvable. So now let's go ahead and solve this right triangle. So here's going to be our right triangle. Let me move this over here a little bit more. There we go. This is going to be triangle ABC. C, once again, is going to be our right angle. And we're given the following information. AC is going to be equal to 2. BC is going to be equal to 3. And that's the only bits of information we're going to find. All right. We're going to label some measurements here. All right. We're going to call this missing side length right here C, little c, right? Because that's going to be the Pythagorean theorem. You use C for the hypotenuse. All right. And then we also have to find the measurement of angle A and the measurement of angle B. We already know that the measurement of angle C is equal to 90 degrees. So we need to find the following information. 1, we need to find what C is equal to. And 2, we need to find the measurement of angle A. And knowing the measurement of angle A, we'll be able to know the measurement of angle B. So for C, this side length C right here, why don't we go ahead and just use the Pythagorean theorem? We already know 2 of the other side lengths, so it will be quite straightforward to plug this into the Pythagorean theorem. So remember, the Pythagorean theorem says a squared plus b squared is equal to c squared. C is going to be right here, and we already know a and b is going to be equal to 3 and 2. So if we say this, we can now plug this in. We got 3 squared, plus 2 squared is equal to c squared. Well, 3 squared plus 2 squared is equal to 9 plus 4. So c squared is equal to 9 plus 4, or c is equal to the square root of 13, which is approximately equal to 3.6. All right, so using the Pythagorean theorem, that's pretty straightforward. All right, and now we can go ahead, we can plug that in right here. So that's 3.2. Let's go ahead and use a different color for our angle B here. We'll use this nice orange color. All right, to find the measurement of angle B, why don't we use one of our inverse ratios? And if we look at the information that is given to us with angle B, if we go, if we go across from B, the side opposite, we have that. And we also have the side that is adjacent. So which trig ratio lets you use the opposite over adjacent? Well, that trig ratio would be tangent. So the measurement of angle B is going to be the tangent of B is equal to the opposite over the adjacent, or 2 over 3. So now if we use our inverse tangent ratio and plug in 2 over 3, that is going to give us some measurement of angle B. And plugging that in on a calculator, you approximately get that the measurement of angle B is equal to 33.7 degrees. I don't know how I just formed a triangle right there. Get out of there. So now we know that the measurement of angle B is equal to 33.7 degrees. And now to find our missing measurement angle A, well, that's, pretty straightforward at this point because we know 2 of the other side lengths. So since the measurement of angle A, since angle B and angle A add to 90 degrees, we just need to solve now for A. So the measurement of angle B is going to be 33.7. We plus the measurement of angle A, and their total is going to be 90 degrees. So subtracting 33.7 across, we get that the measurement of angle A is equal to 56.3 degrees. Approximately equal to, that is. So I will leave this screen up for just a second. If you want to look at that, if you go back and watch this on YouTube, you can just pause it. But just so you can see everything we did there, we're going to do a very similar example. So this first example, we were given 2 of the side lengths. This next example, we're going to be given 1 side length and 1 acute angle measurement. So we'll go ahead and do that one right now. It doesn't require a whole bunch of room. So we're going to go ahead, draw our right triangle. Make sure that's a right angle there. We'll plop down our right angle right there, and we're going to call this triangle HJG. And the only pieces of information we're given is that angle H is equal to 25 degrees and HG is equal to 13. We're going to go ahead and throw down some unknown measurements here. So we're going to use G as an orange. And then we're going to say that HJ, we're going to call that side G. We're going to give that a nice purple. And then we're going to go ahead and say that, there we go, we could use this color. Side H right here, that's also going to be an unknown. So we need to find the following pieces of information. We need to find the measurement of angle G, side length G, and side length H, little g, little h. Well, the measurement of angle G, that one's going to be really straightforward because we know that a triangle adds up to 180 degrees and we're given two of the angle measurements and we know that the two acute angles are complementary to one another. So the measurement of angle G is just going to be equal to 90 degrees minus the measurement of angle H. And if you substitute that in, that's going to be 90 degrees minus 25 degrees, or the measurement of angle H is equal to 65 degrees. So that one is, pretty straightforward. And then we can use trig ratios to find G and H. So it doesn't matter which one we start with. We can go ahead and start with H. Let's start with H. So if we look at H and go to the angle that is across from H, that's going to be this angle right here of 25 degrees. All right. And if we go opposite, right, so that's going to be opposite, over hypotenuse, right, opposite over hypotenuse, that's their sine ratio. So the sine of H is going to be opposite over hypotenuse, or little h, over 13. And so now we just have to solve for h like we did last time by multiplying 13 over to both sides. So 13 multiplied by the sine of h, well, the h is equal to 25 degrees, is equal to little h. And plugging that into a calculator, you approximately get 5.5. And now at this point, you can either use the Pythagorean theorem, or you can just use the cosine of angle H, because this guy right here is adjacent, and over hypotenuse, adjacent over hypotenuse is going to be cosine. So the cosine of H is equal to little g over 13. Multiplying 13 to both sides, we get 13 multiplied by the cosine of H, and H is equal to 25 degrees. Is going to equal G. Plugging 13 multiplied by the cosine of 25 into a calculator, you approximately get that G is equal to 11.8 units.